So the multi-data center support can also be used for other purposes. First one is a typical use case. You have your live data center, which is where your production applications are running, and then you have your your analytics data center where you can run all your Spark or Hadoop jobs, MapReduce jobs. So you write to one, it gets replicated to another, and then you run your analytics in there. This is how typically you would deploy it in Oracle. You would have active for replication within data center. One data center, you would have data guard, right, within one data center, and then you would have Golden Gate to go across data centers, and then for every product that you use, you have to pay Oracle a lot of money. But in Cassandra, you don't have to do anything. And here's the nice bit: you can have your data centers partially in, well, you can have your data centers partially in the classical way, and some of them can be in the cloud. If you want more capacity, some of them actually do it. Some of the e-commerce vendors, when they have like, well, you know, this Black Friday, Cyber Monday peak, or the Christmas peak that comes in, oh, we need more capacity. What they do, okay, we temporarily hire a cloud, we put a replicator data on the cloud, and once that need is not there anymore, disappear it, get rid of it. So that's another way. So it can partially be in the cloud and not entirely. And well, this is another bit that they are trying to say. If you go and look at, there's actually a link to it. I stole this picture from Cloudera's anti-fraud reference architecture. If you're going to do anti-fraud, this is how your systems would look like. But if you're doing it with Cassandra, because, well, DSE, the enterprise edition, obviously, because the data locality comes out of the box. You have your data in Cassandra's nodes. A Cassandra node is just an instance of Cassandra, and the Spark instance also runs on that particular node. So you have data locality, so you can actually benefit from it without doing anything. More on it later. So let's go and speak about a bit of history. So there was a paper by Amazon for the DynamoDB, and then there was also another white paper by Google on Bigtable. So guys at Facebook, well, they took both these white papers, and then they made an open source product called Cassandra, which was open sourced in 2008. Okay, well, enough of very high level talk. Let's go into a bit into the internals, because I like to get into the details. Right. Now, well, a Cassandra cluster, well, is going to have several data centers. So when I use the term cluster, it can have n data centers. So that's the very high level. Sorry, it's written in the other way around. So let's go from the node then. A node is just an instance of Cassandra. So if your machine is running an instance of Cassandra, then that's a node. A node, well, let's stick to this idea. The next one is rack. Rack is a set of nodes, and then the data center, which is a logical set of racks, and then you have the cluster as shown in the picture, right? So now, how does data get distributed? That's, well, you say you write to one node, it doesn't matter which one, because you can, because there is no master, you can pick any node in the which belongs to the ring and start writing data. How does it actually get distributed across all the nodes in the cluster? So the answer to that question is what is it called? Consistent hashing. So that they actually used to use MD5 for consistent hashing previously, if you look at 1.2 and before, but now they are using murmur3 hash function. What they do is they take a primary key, which could be like 12345 or whatever it is, your email address. They send it to a murmur3 hash function, and then you get a number like that. And then what they do is, then if you have a ring with n nodes, this is a very simplistic view, obviously. So you have a ring with n nodes. So this is node 1, 2, 3, 4, 5. They say each node is responsible for a range of this hashed value. So you take your primary key, you hash it, you get a number, and then it says, okay, this number falls into this range. You'll see an example. That's how it works. So how does the consistent hashing work? So, well, this is your table, the classical table. You have some names in there, and then these names are passed on to the Murmur3 hash function. These are real values, by the way. I did it myself, so it's not just some rubbish. What you do is you first compute the hash, and once you compute the hash, you say, hey, I have a cluster with 4 nodes, and each node is responsible for a hash range, and that hash range goes from the value 2 to the power minus 64 to 2 to the power 64. It's quite a large range. And okay, then Johnny goes into node 1, Jim to node 2, Susie to node 3, and Carl to node 4. And the reason why it's called consistent hashing is because once you throw data in, it's not that one of these nodes will have more data compared to that of other. The data will be evenly distributed, so the load's evenly distributed. And then on top of it, you have replication. So normally, let's say if Johnny is in node 1, and if there is a replication factor 3, then you will also have Johnny in node 3 and 4. Right? So far, so good?
What happens if you later want to add more partitions?
Very good question. I'm coming there.
Same question actually.
Right. So I knew exactly those questions would be asked, which is exactly why we have the concept of virtual nodes.
If you have a replication factor 3, that means you have a minimum of 3 nodes that have the data, but the
right.
goal is to have a replication factor of n.
Yes. Yes, 3 is the default number, so I'm just going with the default 3, but you can choose. You can have absolutely 0 replication factor, which means, yeah, you are okay with losing data. But if you're overly paranoid, you can have the replication factor depending upon how much nodes you have. You know, it's all configurable. Okay, well, there is this concept of virtual nodes. Normally, the way I actually told you, you know, where you have, that was easier for me to explain, because if I go into this picture at the very beginning, you'd be lost. If you do want to read about it, I know that Rake also does the same thing. It's the same concept in Rake. So each range over here, like A, B, C, D, it's not like a, you know, a contiguous range. It is actually split into several sections like this. This is again, and one node is going to be responsible for A, F. The top part is without virtual nodes, and the bottom part is with virtual nodes. So you can see that A is the primary ownership, and then it also has the other replication F and E over here. But in here, it is not that, because it is split into a smaller bits, and then each node is responsible for 1 here, 1 there, 1 here, 1 there, something like that. And as you add nodes and as you remove nodes, it is easier for it to scale. It's a bit complicated to explain all of that over here, but you can look it up on how vNodes work, virtual nodes work. It is enabled by default in Cassandra 2.1. Okay.
You don't have to manage the vNodes yourself.
Sorry?
You don't have to manage it yourself.
No. You just add nodes. I have slides over here where I actually create a cluster with 2 nodes, and then I added another, and then the data will get evenly distributed over time. It's not going to happen right away. It's going to happen, though. Okay, let's move on with.
Sorry, one thing.
Yeah.
Does this representation take into account where your data physically is?
No.
So it can happen that I have a rack with 3 nodes, and I have another data center with 100 nodes. It can happen that all data is on these 3 nodes.
You are
that rack dies.
Well, yes. We're going to get to that on the second part. This is where if Cassandra differs significantly from HDFS, or I'm going to get there, yeah, but please stay with me. We're going to go very simple right now and progressively more complex, right? So let's talk about consistency levels. So when you, well, let's say you have replicated data. So then what you do is you primarily read and write data. So how do you know how do you know that the data is consistent or not? Because the weakness of Cassandra is consistency in the CAP theorem, right? So here are the three consistency levels, one, quorum, and all. We're going to go through some pictures in order to illustrate what it is. So what happens is, this is the client. The client is writing to one node, which is the replication factor for, well, let's say the replication factor is 3, and the consistency level is 1 for write and 1 for read. Then what happens is, while the client writes, it writes to one node, and while the client reads, it writes just from one node. It doesn't read from more than one node. And then behind the scenes, what happens is that there is replication from this one node to the other second and third nodes, and then eventually the data will be there across your replicated nodes. So this is the consistency level, 1 for write and 1 for read. And the next one is quorum. Quorum is just a fancy word for majority. So with write 1, the write is always done to just one node, and for read, because replication factor is 3, 2 out of 3 is majority, so it writes to so it reads from majority of nodes, and the data replication goes on behind the scenes. And obviously, write 1, read all. I don't believe I have to give an explanation for that. It's quite self-explanatory. And then write quorum, read 1. Yeah. Well, the question over here, well, this is the best part. This is what DataStax or the Cassandra community always recommends. When you write to the majority of nodes, and when you read from the majority of nodes. So what happens is that the one with the latest data always wins. So let's say when we write to node 1 and 2. When we read from node 2 and 3. We see, hey, node 2 has the latest data because it has got a timestamp attached to the data. The data is more, you know, it's carrying a higher date timestamp, so that is going to win. That is why the quorum is a recommended approach. But I believe there is another recommended approach, because writes in Cassandra are about 10 times as faster compared to that of reads. So I would say write all and read 1 does a brilliant job. We're going to get to that in a bit.
So the timestamps, how are they managed?
We're going to see that. We're going to see that right now. I'm just giving you a little bit information so that in the next slides I'm going to cover that, right?